Linearly independent and linearly dependent vectors. Dear students, if we are given a set of vectors from a vector space, then these vectors will be linearly independent or linearly dependent. Now, to determine whether these vectors are linearly independent or dependent, we shall put this linear combination equal to a zero vector. And from this we shall get a system of equations. We shall solve the system of equations to obtain the values of C1, C2 up to Cn. If we get that all the constants are zero, then we shall say that these vectors are linearly independent. And if we get that at least one constant C1 or C2 is non-zero, then we shall say that these vectors are linearly dependent. Let us explain it by some examples. In this example, we are given two vectors, v1 and v2. They belongs to R square. Let us determine whether they are linearly independent or dependent. So we shall put the linear combination C1 V1 plus C2 V2 equal to a zero vector. Let us put the values of V1, which is 1, 2 plus C2, putting the value of V2, we get 2, 3, which is equal to a zero vector 0, 0. Let us multiply C1, so we get C1, 2 C1 plus multiplying C2, we get 2 C2, 3 C2, and this is equal to 0, 0. From this we get a system of equation C1 plus 2 C2 equal to 0 and 2 C1 plus 3 C2 equal to 0. Let us solve this system of equation by the Gauss elimination method. So the augmented matrix is 1, 2, 0, 2, 3, 0. Now we need that this 2 must be 0. So let us subtract 2 or 1 from our 2. We get 1, 2, 0. Now this one is 0, this is minus 1, and this is 0. In the next step, we multiply row number 2 with minus 1. So we get 0, 1, 0. Now by backward substitution, we get C2 equal to 0. And then from the other equation, we get C1 plus 2 C2 equal to 0. But as C2 is 0, so we can write that C1 plus 2 into 0 is 0, which is equal to 0. From this we get C1 is equal to 0. So we can see that both constants C1 and C2 are zeros. So this implies the vectors V1 and V2 are linearly independent. In example number 2, we show that the given three vectors are linearly dependent. In a similar procedure, we shall put the linear combination C1V1 plus C2 V2 plus C3 V3 equal to a zero vector. Let us substitute the values of V1, V2 and V3. So we have 1, 2, then plus C2, here we have 1, minus 1, plus C3, here we have 1, 3, which is equal to the zero vector. From this we get C1 plus C2 plus C3 comma 2C1 minus C2 plus 3C3 equal to 0 comma 0. From this we get a system of equations. C1 C2 plus C3 equal to 0 and 2C1 minus C2 plus 3C3 equal to 0. Let us write the augmented matrix. So we have 1, 1, 1, 0, then 2 minus 1, 3, 0. Now we need that this number should be 0. So let us apply the row operations. R2 minus 2 R1. So we have 1, 1, 1, 0. From here we get 0. Here we get minus 3. And here we get 1 and this one is 0. Now this minus 3 should be 1. So let us apply another row operation. We write 1, 1, 1, 0. And then we multiply row number 2 with minus 1 over 3. So we have 0, 1, minus 1 over 3 and 0. Now by backward substitution, we have C2 minus 1 over 3, C3 equal to 0. Let us say this is equation number 1. Then we have C1 plus C2 plus C3 equal to 0. This is equation number 2. Now from 1 we can obtain that C3 is equal to 3C2. So here we let C2 equal to some non-zero real number t. Then C3 becomes equal to 3t. Now using the value of C2 and C3 in 2, we get C1 plus C2 is t and C3 is 3t. This is equal to 0. From this we get C1 is equal to minus 4t. So we have C1, C2, C3, which is equal to the value of C1, that is minus 4t, the value of C2, that is t, the value of C3, that is 3t. Let us take t as common. So we have minus 4, 1, 3. So for any non-zero real number t, we have different solution of this system. So we can see that the values of C1 and C2 and C3 are non-zeros. So this implies that the one solution of this system is C1 is equal to -4, C2 is equal to 1, C3 is equal to 3. But this system has an infinite number of solutions. So this implies that the vectors v1, v2, and v3 are linearly dependent. That's all.